Yeah.
So it's
Okay.
my great pleasure to introduce Dr. Alex Alemi from Google Research. Alex is a senior research scientist at Google Research, and he has had quite an interesting path on his way to this position at Google. He got his undergraduate degree in physics from Caltech in 2009, where he wrote a very interesting undergraduate thesis with the title, Why Venus Has No Moons. And after this, he moved to Cornell University for his master's and PhD, where he worked with Jim Setna. And in the spirit of staying interesting, Alex's PhD thesis over there was called Zombies Reading Segmented Graphic Articles on the Archive. And after this, Alex moved to Google Research, where he's now senior research scientist in machine perception. And he's at the frontier, as you will see today, of really thinking about machine learning algorithms, which are practical, but that's just one side of the story. He's really bringing in his years of thinking about physics and connecting machine learning in very unique ways with concepts from physics. And also, I want to point out that Alex has very kindly offered to meet with some of us for half an hour slots informally later today and tomorrow. Some of them have already sold out, quote unquote. A couple of slots remain, so they are going to be on a first come first served basis. You can email me or send me a direct message in the Zoom chat. So with that, so this talk is being recorded. If you don't want your video to show up or anything like that, you can remove your video. And Alex, the floor is yours.
All right. Thank you very much, Pratyush. So I have a little interesting setup technologic here. I wasn't able to get the video on my laptop to work, so I've also got my phone. So I think I'm kind of logged in from two places with two different usernames, and my video is going to be coming from one, and the audio and the presentation is going to be coming from the other. And also, if I'm like not looking at the camera, it's because I've got three screens in front of me now, so it's even more awkward than these things normally are. So I apologize for that. But hello. I'm Alex Alemi. I am a senior researcher at Google Research. I'm a kind of reformed physicist, now doing machine learning these days. And today I wanted to kind of talk to you about some of the things I've been thinking about, going back to like a workshop paper that I wrote, and sort of some of the relationships between machine learning and thermodynamics. So in particular, let's see if this works. There we go. Hopefully there we go. Okay, so as I sort of outlined, what are we going to try to do? First, I'm going to try to actually just talk about thermodynamics, but maybe from a perspective that you're not used to hearing it about it from, sort of a probabilistic perspective, or one might say, thermodynamics from like a machine learning perspective. And then once we do that, once we lay the groundwork, then we can talk about machine learning from a thermodynamic perspective, which is really sort of central to a lot of the work that I have done with colleagues. And time permitting, we'll be able to talk about some of those applications and some of the areas where we've been able to kind of make improvements over existing techniques. So to start, let's talk about thermodynamics. I guess what I really like about thermodynamics is it's sort of a physical theory without necessarily any physical basis, right? Like it's fundamentally just the statement about trying to describe what happens in complex systems that are sort of too complex that you can't describe any of the individual pieces or any of the individual components. And yet there are strategies by which, even though we can't describe microscopically what's happening in a system, we can still make very accurate predictions about how certain properties or certain questions we might ask about the system evolve over time. And that's what thermodynamics allows us to do. If you haven't read it before, sort of a lot of the kind of philosophy about what I'm about to discuss kind of goes back to this fantastic article by E.T. James, Information Theory and Statistical Mechanics, a sort of information theoretic perspective of statistical mechanics. We'll focus on sort of the thermodynamics here. But if you haven't read it before, it's a great article and a really sort of eye-opener. It's a unique way of thinking about it, especially distinct from the ways that it's normally presented in undergraduate and graduate courses. So, okay, so let's try and do some thermodynamics. What do we start with? We start with a physical system, and the physical system has a state. And by state, we really just mean a complete description of the system. Everything you would need to know to describe precisely what configuration the system is in. To give some examples, right, the classical example is something like an ideal gas, and at least for a classical gas, the state of the system could be described by writing down the positions and momenta of all of the, Avogadro number of particles in some box. So the states, for complex systems, these are big objects. These are huge. I mean, I would challenge you to actually write down, 10 to the 26, vectors of positions and momenta. That itself is sort of an impossible task. But in principle, if you wanted to classically describe the system exactly, you would need to know its exact configuration, and that would mean describing exactly the position momenta of all of those gas molecules. Another thing you might be familiar with is the Ising model. If you haven't heard of it before, don't worry. You just think of like a chessboard or a grid of squares where every grid has a coin on it. And you could imagine a system where what you're trying to describe is for every one of the squares, which of two states it in. Is it heads or tails? Is it on or off? Is it black or white? And this is a system. I mean, it's a model that especially people in system mechanics like to use because it models like magnets. But I'm just giving it as another example of a physical system. Here's a model, but with a state, right? And here the state would be a complete description of the system. For every one of those squares, you need to tell me whether it's positive or negative, whether it's heads or tails. So in here, I've got a picture. It's 128 by 128 pixels. I think that's 13,000 squares. And for each one of those 13,000 squares, I would have to give you a yes or no, a Boolean, a true or false. This is just one state, right? But there are many. And there are many that kind of look very different. This one kind of, you see sort of clusters, it looks like. Here's another completely valid state. It's another list of 13,000 yes or no's. This one happens to look sort of random. Here's one that looks more sort of clustered, more globular. And finally, here's one that you might think looks particularly structured, right? But in terms of states, in terms of the model, this is the same as all the rest. Is this actually showing up on my video?
It flickered. You had the clustered face separated one. It flickered and went away.
Flickered and went away. So you guys aren't seeing, right now it's supposed to look like the University of Maryland.
Yes,
logo.
now it does.
Oh, excellent. Okay.
Cool.
All right. So the slides are kind of slow to load, and hopefully that won't persist. But if it does, we'll see. Okay. But anyway, so here's just another configuration of that same system, right? This one happens to look as though it has a tremendous amount of structure, but again, it's just sort of 13,000 yes and no's, ups and downs. Another kind of system that we might consider would be a neural network. And for the present purposes, you should think of a neural network as just being a function approximator. You should think about it as a thing with a billion knobs, and as you adjust those knobs, you achieve different functions. Oh man, my slides seem to be really slow. I can sort of see them in the corner of my one screen. But okay, so for a neural network, considered as a sort of system, what's the state? The state of the system is going to be the setting of all of the parameters of the neural network, all of the knobs, all of the weights, all of the parameters, all of the coefficients of this thing. If you sort of don't know what neural networks are, let's talk about that for a second. What is a neural network? For both this talk and life in general, you should think about a neural network as just being a rich function approximator, a thing with a billion knobs. When you adjust the knobs, it approximates different functions. And in fact, you should think about it as a more or less universal function approximator, something that has a setting of the knobs that can approximate any function you desire, and one for which we have efficient techniques to search in the space of all possible functions, all possible settings of those knobs. Themselves, they're quite simple. They're a sort of way to build up simple pieces that can make expressive and complex predictions. And we can kind of like walk through that sort of quickly if you haven't seen neural networks before. So neural networks, they're called that because the sort of atomic unit, the basic thing in the system is what's called an artificial neuron. They're called that because the people who first studied these things studied them as a model of what was supposed to be a model, like a mathematical model of a biological neuron, one in your head. But you shouldn't take that association too seriously. Think of it just as a particular sort of model or mathematical object. And so, what is a biological or an artificial neuron? It's a function, a particular function between some number of inputs. It looks at a whole bunch of numbers that come in, and it predicts one number as its sort of output. And in particular, the way that it approximates that, the function that it actually computes is it has a single sort of coefficient, a single weight, a single parameter, a single multiplier for every one of its inputs that it multiplies the numbers by. It adds them up, and then it adds a final parameter, a final bias, a final number to the result. So it's really just all an artificial neuron does is it takes a weighted linear combination of all the inputs. The thing that's sort of magical, the one sort of extra bit, the reason that this isn't not interesting, the reason it goes beyond just being a linear combination of all the inputs is we apply some function to this result that has to be nonlinear. That sort of sound complicated, and the one that people typically use is a thing called ReLU for rectified linear unit. a very big name for something very simple. All the nonlinearity that people use, probably most common even to this day, is this one. All it does is a sort of thresholding operation. If this weighted linear combination of all the inputs is negative, set it equal to 0. If it is positive, you just sort of do the identity function. So it's this sort of simple sort of thresholding operation. That's it. An artificial neuron is just this particular sort of mathematical function, a weighted linear combination of its inputs that are thresholded with some function. If we can do this once, we can do this a bunch of times. And a layer in a neural network is really just a collection of these artificial neurons with different weights, different coefficients to the same inputs. So this allows you, distinct weighted linear, thresholded weighted linear combinations of the inputs. You could do it n times, you could do it a bunch of times, and each one would be slightly different and would respond in different ways. They'd be 0 in different places. And if we can do this sort of once, and we can make one layer of this thing, once we are computing numbers at each one of these artificial neural neurons in a layer, we could do it again, and we could now like stick another layer on top. And that's all that's all a neural network is you kind of recursively build up a single function, which is composed of these things all connected together in some big network. And that's really it. That's how you actually build a neural network. It isn't sort of more complicated than that. All the sort of alchemy, all the magic, all the like terms of art and things have to do with precisely the ways in which you connect these things, precisely the ways in which you wire up this diagram, particular choices of nonlinearities and particular choices to initialize this thing, things like that. But in the end, you should think of it as it's really just a sort of a parametric function. Think of it as like a fit, like a polynomial fit. It has a particular sort of compositional and recursive structure, but that's all it is. You now have all of these knobs, all of those weights, all of the matrices and vectors that go into this function. If I adjust them, like if I adjust the number on each one of these lines, then I change the output. It's a different mathematical function. And the sort of neat thing about neural networks is they are very expressive. So in particular, like here, let's try and visualize one of them. It'll be, I'll take a one-dimensional input. I'll just take a number on the real line. I'll send it through a couple layers. In fact, I'll actually send it through a neural network that looks like this diagram with 128 neurons in each layer with the ReLU nonlinearity. And then I have it go to a single neuron at the output, and I'm not even going to apply the thresholding so that it's just a linear combination of the other guys. And I get a function approximation that we can visualize with a graph, like a plot. And so now if I set each one of those coefficients, it is a particular function. And if I set them to a different set of coefficients, it's a different function. In this particular case, I happen to be using, I wrote it down somewhere, 131,000 coefficients, 131,000 parameters, each of which is a 32-bit float in the machine. So there's like 500 kilobytes of just memory in the machine. You flip all of those bits and you get different function approximations. Here's some examples of what it would do if you just sort of randomly initialize it. But just like the sort of icing model that we saw before, there's all of these sort of like twiddly, weird looking functions, but then there's also a whole bunch of specific ones. And in particular, like here, this looks like it's cosine of x, but this is the same neural network. I just happen to find some setting of those 131,000 numbers so that the function that the neural network, approximates is indistinguishable from cosine of x. And you can do this with basically any function. That's the neat thing about neural networks. It's an expressive family, and not only does sort of all functions you can think of live in this space, but you can find them. And so here I tried to come up with some function, the sine of x squared over 4 plus sine squared of x over 2. And I even, set it so it was 0 less than 0. And again, like this isn't that function plotted. This is actually the neural network where I happen to find a setting of those 131,000 coefficients to make it look exactly like that function. And for Maryland, you could even draw an M. Again, we should think about this. It's a complicated system, right? What is the state? The state is all of the parameters. It's the values that all of those coefficients take. And once that's specified, then it, I could kind of probe it. I could see what the thing does. As a final example, maybe a simple one, we could have a simple system where the state isn't a high dimensional object. It's one dimensional. Let's imagine just like a ball on a spring where even a heavily damped ball. Like let's imagine something that's just one dimensional. I literally just have a single number, which is where I am on the real line. That's going to be my state. Just because this is a system in which I'll be able to actually like plot things because it's simple enough. Okay, so that was a lot of talking, but what do we have now? We have the first step. Thermodynamics is about describing physical systems. Physical systems have a state. The state is a complete description of the system. It was already very difficult to write down the exact state of a system. In fact, impossible for certain systems like an ideal gas. And honestly, we don't care. Oftentimes, we don't care about the precise position of the 47th atom in the box. All we care about are certain functions of that state. There's certain properties, certain questions that we actually care about. And these are the state functions. They are literally just functions of the state. There are things that you could compute. If I gave you the complete description of the system, there are certain questions you could ask that you could compute if you knew the exact system. These are state functions. The classic examples are things like energy or number of particles or volume or length for a wire or magnetization for a magnet or training loss for a neural network, say. These are things that if I gave you the exact specification, you could calculate. And these are often the things we actually care about, these state functions. Interesting questions about the state. Okay. Classic example physically is the energy, right? If I give you the exact state of the system and you know it's Hamiltonian, you could calculate the energy of the system. For my one-dimensional example, let's imagine that it's attached to a spring, so that if I give you the position, you can calculate the energy, and it's just a quadratic, x squared function. For something like the icing model, the actual Hamiltonian asks you to look at all possible pairs of guys who are neighbors and whether they agree or disagree. You get +1, -1. But there's other state functions you might care about, just things you care about. For the icing model, you might care how many black things are there total. And so you could add up all of the black squares, and that would be an example of a state function. Given the values of all the 13,000 things, I can just count how many are black. There we go. Okay. It's already hard. It's already difficult. It's already impossible in certain cases for me to write down the state of a system. We're actually going to make it a lot harder, because what I'm going to do is I'm going to admit the fact that I don't know what state most of my physical systems are in. Like, I can't write it down. I don't have that kind of knowledge. I can't take that many precise measurements. And so I'm going to try to describe my belief about what state the system is in next. I'm going to try to describe what I do know or how much I know about what state the system is in. The first thing I want you to realize is that this object, a distribution over all possible states of the system, is a much, much, much larger object. It was already sort of impossible to describe even the configuration of a system precisely. This is something defined in the space of all possible configurations. So for something like the icing model, where we had discrete states, the set of all possible states is a much more massive object. It was already sort of hard to write down 13,000 yes and no's to describe one of these pictures. How many pictures are there? There's 2 to the 13, or yeah, 2 to the 13,000. 13,000 seems too big. 2 to the 13,000 possible pictures, an astronomical number. And to describe a distribution over that thing would mean to assign a probability to every one of the possible pictures there could be. Now, that's a much larger space of possible things. Even for something that was seemingly simple, like our one-dimensional ball example, the state is now a single number, but it was a continuous number. And so the space of all possible distributions over the continuous number is an infinite number of numbers. It's a function. It's a distribution. It's a probability distribution for where we might find the ball. And there's a lot of them. There are, ones that kind of look smooth, like a Gaussian. I could say, oh, I don't know where it is, but it's somewhere near the center. There are ones that are very specific. I could put all of the mass of the probability distribution on a single state if I knew exactly what state it was in. Or it could be sort of anything in between, weird multimodal things or disconnected things. All of these go. Okay, we took something that was hard, we just made it even harder. But there's one thing that we can do. We can invent a new number, a new quantification, a new thing that we can compute, which is, I would like to be able to describe, ultimately, we'd like to come up with simple descriptions of the system, simple sets of distributions over all possible states. And so I need some way to measure simplicity. I need some way to measure simplicity. And, oh, I'm skipping ahead. And we can do that. So how do we measure how simple the distribution over all possible states is? Well, Boltzmann and Shannon gave us an answer. It's the entropy. There's a number that I can calculate. If you give me a distribution over all possible states, if I just compute, P log P, I sum it up over all the states, that's called the entropy. And this, as a number, tells you sort of how much information there is in the state, how complicated it is. It's a way to quantify your sort of degree of ignorance or your degree of how specific your belief is, how many questions you would need to ask in order to recreate that set of beliefs. Unfortunately, Boltzmann and Shannon got it a little bit wrong. The entropy is useful, but it doesn't work for continuous distributions. You can see that because it's sort of dimensionally inconsistent. Once you go to sort of continuous spaces, the probability distribution is a density. It's a thing that when you integrate it, you have to get a number. And so whatever the sort of volume element of your space is, the probability distribution has units of like 1 over volume. And then what's the log of an inverse volume? I don't know. And that's a signal that the entropy is sort of wrong measure for continuous distributions. But there's sort of an easy fix. And the easy fix is to realize that for continuous distributions, or honestly, even if we were doing discrete distributions, it's not, you can't really say how complicated a distribution is. What you can say is you can talk about how much information there is in one distribution relative to another. Once I turn this into a ratio of two things that are inverse volumes, that's dimensionless and the whole thing works. This is a log of a dimensionless number. This is a volume integral of a volume element. We're okay. So this is the relative entropy, or the KL divergence. And this really is a way to quantify how complex a set of beliefs are, how much information is contained in a distribution, albeit only now in reference to or with regards to some target, something that you specify as having no excess information. This is the KL divergence, and it's the sort of central quantity, the central measure in all of information theory. Mathematically, it is guaranteed to be positive, which is a very useful property to have. Okay, we went from states to distributions over states to now some way to quantify how complex a distribution over states would be. What are we going to do with our state functions? Those were defined for a particular state. Well, given a distribution over states, I could now ask not what the value of the state function is, but what's the average value of the state function? If you tell me that you think it's in all of these states with these different weights, I could take the weighted combination of the value of the state function on each of those states and compute the expected value of the state function. And so those are sort of well-defined. So we do this. And let's do our simple ball example. Now, what was the state? The state was a single one-dimensional number where I am in the real line. The distributions over all possible states are all possible one-dimensional distributions of positions. But what I can do is I can create a graph, and I could sort of, in the space of all possible distributions, measure, if you give me a distribution, I could measure the average energy. I could also measure the KL divergence. Those are two things I could calculate. And so let's start with one thing, and we also need to choose our target. We need to choose the thing that we measure with respect to. So let's imagine we start with a Gaussian distribution, and we're going to call that the Q, both the P and the Q in the KL divergence. Now, the KL divergence of a thing to itself has to be 0, so the KL divergence is going to be 0. We can also calculate the average energy of this thing, and for our ball with square, it turns out to be 1. This gives us a single point in this two-dimensional space. We could do it for any distribution. Here's another one, right? The one where I definitely knew it was at position 2. Well, I know the energy, 2 squared is 4. What's the KL divergence? Well, the KL divergence, how much information is contained in the state for any sort of delta function, is infinity, because it takes an infinite number of questions to kind of describe a real number exactly, right? It has an infinite number of decimals. So that's kind of way up there off our chart, but at some known energy. For some of these other ones, like this one, some weird multimodal distribution, again, I just calculate the average energy under that distribution, the average of this thing, as well as the KL divergence. It's a kind of thing I can compute, and it turns out to be right over here. For this one, this weird bimodal thing, it's some other point over here. And now we can ask, in the space of all possible degrees of belief, all possible distributions over all the states, what do we get? Well, you start perturbing these things, and you start sort of filling this diagram, and you keep going, and you discover that you sort of fill the whole space. But interestingly, you don't fill the whole space. There's a boundary, there's a line, there's a sort of surface of states that are optimal, that are maximal, that are least informative. There's some special states that are unlike all the rest, that sort of live on the boundary of this whole plane. Those are the equilibrium states in thermodynamics. Those are the simplest states. Those states are the solution to a particular problem. You can imagine finding them by saying, like, if I want to find some point over here, I could do a constrained optimization problem. If I know that the average energy is fixed to be something like 3.7, I could search in the space of all possible distributions in principle for the one that has the minimum possible KL divergence, but has that expected value. And I would pick out a single point on this edge, that one. I could do it again for some other fixed energy, and I could pick out some other one over there. And I could do this for all possible energy values, and I could end up describing the points on this surface. Instead of thinking about it as a constrained optimization problem, you could think of it as an unconstrained optimization problem by doing like a Lagrange multiplier. And this, hopefully you've seen that in some of your math classes or something, but you kind of add a coefficient here. And now for all settings of that coefficient, you can trace out all the values on this edge. You can actually interpret this thing geometrically as well. Like when you do this beta ends up being like if you did this with some fixed beta, you'll pick out a point on the surface where the tangent line to that point on the surface has slope beta. Or you can really just think about what this is doing as a way of parameterizing the curve. Is now I end up like, I try to rotate the curve and I ask for the minimum of all possible rotations of the curve. The amount of rotation is the beta, and I minimize it everywhere. I'll be able to trace out this curve. Because interestingly, this KL divergence function, it has to be convex in its argument, in the sense that this thing is always going to have an edge, and this edge can't double back on itself. That's sort of a mathematical property of a KL divergence.
A quick question. This edge depends on your choice of Q, right?
Technically, yes.
What do you mean by technically?
I'm going to say yes.
Okay, so for different choices, but of course, what we think of as the equilibrium state doesn't depend on Q. I would set Q equal to 1, but that's not normalizable. Are you going to be talking about this, or is this not particularly relevant for what you have to say? And if that's the case, that's fine. We could drop it.
Yeah, so I don't want to go into too much detail right now. I mean, I think you're asking an interesting question, and I think it has an interesting answer. So you're right that normally in quantum mechanics, in thermodynamics and stuff, we're used to taking Q to be just like 1, which is equivalent to a uniform distribution on the space, sort of unnormalized. And that's what we use in physics, but there's a reason, right? And the reason is basically, I think I'll just say this, and then maybe we can talk about it later. But in thermodynamics, basically, the reason that this surface is interesting is because under any sort of random dynamics, under any sort of Markov process, you are guaranteed to sort of, the amount of information you can retain about the initial state is always going to kind of go away. And if not only you have a Markov process, but you have a stationary Markov process, meaning that there is some distributions that are constant under this dynamics, then you're also guaranteed that monotonically, the KL divergence with regards to the stationary state has to monotonically decrease. Really, all I'm trying to say is there's something special about these edge states. Not only are they sort of minimally informative, but in the real world, if I just set a thing on the desk and I wait, nature does its course and it kind of acts on it with random fluctuations. And those random fluctuations have the effect of removing sort of information from the state of the system and always driving it towards an edge. And that edge is an edge that's sort of special given the dynamics. But the fact that in physics, Hamiltonian dynamics are volume preserving on phase space is the reason why a uniform density on phase space is the sort of right cue to use.
Thanks.
I don't know if that helped, but yes. Okay. The last sort of bit is, even though this seems like an impossible problem, we took a hard thing to write down. We considered the space of all possible things you could write down. And then we tried to consider some, measure of how hard it was in the space of all possible things. And we determined that there was some kind of edge. We mathematically could describe that sort of edge. And interestingly, formally, this thing has a solution, like a closed form solution. Like you can write down, you can characterize all of the states on the edge in some like closed form. And it might be recognizable as a Boltzmann distribution. Like mathematically, if you do calculus of variations and you minimize this problem, you get a distribution that looks like this: Q over Z e to the minus beta E, where this is the state function that you had a constraint on. This is the Lagrange multiplier. This is the thing that you chose as the base, and z is the normalization constant. If we need this whole thing to integrate to 1, we need this to be a number such that if I integrate this whole thing, it's 1, and I can just set it equal to the integral of the numerator, guarantee that it integrates to 1. Boltzmann distribution is the solution to a very particular problem, namely, how do we characterize this surface, this boundary of extremal states? You can do this for not just one constraint, right? I do one constraint because then I had a two-dimensional picture and a one-dimensional surface. But if I had other constraints, those would just be sort of other axes. But the whole story would be the same. There'd be some n-1 dimensional surface of states that are minimally informative or closest to the target, subject to the constraints. And we can characterize that as well. And it turns out to be a generalized Boltzmann distribution. And this is, in thermodynamics, things like the canonical, the grand canonical, the microcanonical, you can switch between all those distributions by just constraining different ones of the state functions, the number, the energy, things like that. So really, in this view, thermodynamics is really just a story. It's about geometry. Given a physical system, given all of its microscopic details, its physics, its Hamiltonian, things like this, and the questions that you're sort of allowed to ask about the system, there is a surface of states that are minimally informative. There is a surface of distributions over states that are minimally informative. And those distributions over states are the ones that have simple properties. They live on a surface, meaning they have some geometry. They have derivatives. Those, like the Lagrange multiplier is well defined on the surface. If I'm up in the bulk, there's no definition of a derivative. And thermodynamics is just the study of this geometric object, this surface. Here is a plaster cast that Maxwell made of a surface described by Gibbs in a paper about water, a water-like system. And it literally is like all of thermodynamics is studying a particular three-dimensional surface. Different physical systems have different surfaces. And all of actual undergraduate thermodynamics is now just sort of a sadistic exercise of all possible different ways you could describe the same object. There's a surface sitting in front of you. And now you do coordinate transformations. Oh, instead of describing every point as being a value of the entropy in terms of the energy and volume, I could describe it as the point of energy in terms of the entropy and volume. I could reparameterize it. Or because it's convex, I could, instead of describing it in terms of the value of the energy, I could describe it in terms of the value of its derivative with respect to energy, aka the temperature. And I could do those Legendre transformations. But again, these are just ways of describing the same object. And in terms of this geometrical object, things are kind of make more sense. Things like Maxwell's relations are just statements that if I move a little bit south on this thing and a little bit east versus I go a little bit east and a little bit south, I end up at the same point. Mixed partial derivatives are the same. And that's what gives you the Maxwell relations. So that is sort of my view of thermodynamics. What is it? You take a system, you consider not just all of its states, but all possible distributions over states, and you look for the ones that are simple. You quantify simplicity by minimizing a KL divergence between the distribution over states and some target. And you make it interesting by setting constraints on a bunch of things that you can measure that you are interested in. And then thermodynamics is the study of the resulting surface of distributions that satisfy this constrained optimization problem. That was thermodynamics, or a take on what thermodynamics is. So now let's try to talk about machine learning, but in the same language. So there's going to be more moving parts, but the story is going to be the same. I just said that thermodynamics, we could study all possible configurations of a system, all possible distributions over configurations of a system, and look for the simplest such distributions over configurations with respect to a target subject to constraints. So we need to identify what is the space of all possible things that we're going to look at? What do we set as a target? And what sort of state functions are we going to use? So not that it's all of machine learning, but a wide swath of machine learning, I think, can be sort of summarized in the sort of 5 variables that are on this diagram. What normally happens? Normally we have a data set. And to make it concrete, imagine you're doing something like image classification. A whole bunch of images come in, and you're interested in saying what's in the image. Oh, this is a turtle, this is a dog, this is a cat, this is a hot dog. So we have one set of objects, which are the images, here represented by this cute turtle. We have another sort of random variable, another set of objects, which are the labels that humans assign to those things. That is a turtle, right? The string turtle. And if we're going to do machine learning, we are going to invent two things, right? We're going to sort of add a neural network to this world. And the neural network, like we said, is like a big function approximator. And in particular, we're interested in neural network. We're going to build a neural network that only looks at images and then sort of spits something out. This representation, think of it as just the output of a neural network that you built. And that neural network has a billion knobs. And those knobs, like we said before, we can identify with another part of the state, the setting of all those knobs, call it theta here. And here I'm trying to show some set of relationships, namely like the data, like the images and the labels. I don't actually get to set those. I don't think that I know the distribution over all images and things. The sort of rest of the universe specifies that. Like I don't get to pretend that I know the relationship between images and labels. But there's a process by which I can collect this data, right? I can sample images and labels from the universe to create a data set. I am going to build a neural network, but I sort of have to specify not just the like individual configuration of an individual neural network, but I need to specify what type of neural network I'm going to build, like how many layers it's going to have, how wide it's going to be, like all of the sort of architectural choices. And I need to specify how I'm going to set all those knobs, right? There's going to be some learning algorithm. There's going to be some code that I write that is going to set all the knobs of the neural network. And that code is going to look at a data set, right? I'm going to write an algorithm that's going to look at a data set, adjust all the knobs of a neural network, and that neural network is, given all the knobs and given any image, going to spit out some representation, just some high dimensional vector. So these are the sort of like people participating in a normal sort of machine learning setup. And so this is the sort of thing that we now need to consider the distribution over all possible configurations of. But this is now an even larger space because now we're considering sort of all possible ways that I could adjust the parameters given the data set, all possible learning algorithms, and all possible neural networks, all possible ways that I could represent an image in some, a neural network, some kind of output. This is the distribution over all possible states that we need to consider. The next step would be specifying some kind of target. And for this, what we want is something, the KL divergence gives us some measure of complexity, some measure of how difficult or how complicated things are. So what we need is some target that we think of as being simple. And so we can choose the sort of normal generative modeling assumption here. What we wish were to be true, like if we actually do a good job, right? I mean, I can choose a random learning algorithm and some random neural network, and it will certainly like spit things out. But the things that spit out are not going to be interesting. What it would mean for it to be interesting is if I could just observe the output of a neural network and use that to predict what the correct label was. Similarly, it would be interesting if I could only observe the output of the neural network and somehow reconstruct the image that went into it without seeing the image itself. And so we can kind of encode that target, like what we want to happen, and take it as the sort of target distribution for this KL minimization and sort of proceed to the next step. Where the next step is we need to decide what functions we're going to measure. And I think there's sort of 4 that are interesting. Basically, we want to consider relationships between subsets of these variables. So one thing we could consider is how much information we sort of extract from the data set and stick into our parameters, like how much information our learning algorithm sucks out of the data. And that's sort of a thing that we can calculate that looks like an entropy. It itself is a KL divergence, but now it's a KL divergence over the distribution of all of the parameters that are algorithm sets with regards to some prior setting of the parameters, before we train the algorithm. And this is one thing that we think might be interesting. How complex is our learning algorithm? This is a measure of how complex our learning algorithm is, a relationship between these 3 variables. Another thing we could ask is, like we said, we'd want to eventually be able to predict what the right label is for an image, given only the output of the neural network. And so we can quantify that, like just ask, like, how well can I predict what the label is given the output of the neural network, and write down the corresponding loss function and call this one of our sort of state functions. We also said we might be interested in trying to reconstruct the image given the output of the neural network. And so we could write down a loss function for that, distortion, how well we can recreate the image given the output of the neural network. And finally, we might be interested in how complex our neural network's representation is. Like, how detailed is the description that comes out of the neural network? How sensitive is it to the ingoing images, and how sensitive is it to our choice of learning algorithm? And so we could kind of, how spiked or how peaky is the output of the neural network? And not that I hope that those, you necessarily know exactly what those are, but I just wanted to say that these are 4 questions that you can imagine asking. If I specify a learning algorithm and I specify some neural network and I sort of ran it a billion times, I could measure the expected value of each of these things: how well I predict labels, how well I reconstruct images, how complex the parameters are, and how complex the outputs are. And so then we can do thermodynamics. We've got sort of a space of all possible things I could do. I set a target, I want to minimize a KL, and I have constraints on things that I thought were interesting. And just like sort of in principle what happened in the simple case, the same thing's going to happen here. We have measured 4 things. We consider all possible sort of trade-offs between those things in the space of all possible learning algorithms, space of all possible things. We start filling a space. There's going to be a boundary. That boundary is going to be convex. And if we wanted to trace out that boundary, we do, Lagrange multipliers. We sort of search in the space of minima of all possible rotations of this surface. And if you wanted to, you can encode that whole thing in a single objective, sort of minimize all 4 of these things that we talked about in terms of setting sort of 3 coefficients, 3 temperatures. And in our actual sort of workshop paper, the whole point of it was that this sort of one description, this sort of one surface, this one thermodynamic surface, incorporates a wide range of existing algorithms that people use in machine learning. And not that I expect that you have full familiarity with this, but just to kind of like talk through them maybe just a little bit. So like in particular, if I take this whole space with these 4 axes and I sort of rotate it so that I only care about how well I can predict images, and that's the only thing I care about, and I minimize just along that thing, I'll get a single point on the surface. And that single point is going to be, the neural network that does the best job of predicting the labels. This is what people normally do when they say supervised learning, try to train a neural network to predict labels as well as possible. But now we understand that that whole setting that people do is a single point on this larger surface. If instead of just minimizing C with all the other coefficients 0, if I added back in the complexity of the representation of the neural network, now I have a one-dimensional family of solutions where I have a sort of temperature that I can adjust, a rho parameter that allows me to trade off between doing the best I could possibly do at just minimization versus it doing the best that I could possibly do at predicting labels, subject to a constraint on how complex my neural network's representation is. And this is actually our paper from a few years ago, the variational information bottleneck. If you kind of rotate the space and you just ask how well I can reconstruct images, and that's the only thing I care about, I pick out a single point on the surface, that would be a way to build an autoencoder, which you may have heard of. This is a neural network that takes an image, spits out some vector, and then tries to take that vector and reconstruct the image. If you, let's say, another single point on the diagram, but I could take R plus D. So this is like asking for, I take the surface and I rotate it sort of 45 degrees so that my R and D axes are sort of just aligned, and I look for the minimum on the whole surface. It's a single point. And that single point is, there's a whole sort of industry associated with finding these solutions. They're called variational autoencoders, or VAEs, which you may have heard of. They're, Bayesian autoencoders. And they had problems. Like, people were training these things and they were discovering that for certain choices of neural network architecture, if all they did was sort of minimize this thing and pick out a single point, they weren't always satisfied with the solution they got back. Sometimes it sort of ignored the intermediate representation and just kind of created gobbledygook images, or sometimes it was, it sort of memorized everything in the image. And we have a paper from a few years ago just kind of trying to point out this part of the story. Like, hey, if instead of just uniformly trying to, pick a single point on the surface, if we realize that there's a trade-off to be made between how well we can reconstruct images and the sort of complexity of the output of the neural network again, we can have a sort of a temperature parameter that we can adjust, and this can itself correct for a lot of the mistakes that people were seeing these networks make. Because now you get to explore a trade-off. How well can you reconstruct subject to a constraint on how complex the representation is? And you can imagine that less complex representations might have more desirable properties, even if they don't do a perfect job of reconstructing images. If you, and I can kind of play this game all day. There's papers associated with individual points or individual sort of edges of this larger surface, like a semi-supervised VAE, or if we go to the other side, you try for the best classification performance you want, but again, with coefficient 1 with regards to the complexity of the parameters. This is actually a Bayesian neural network. And it's exactly the objective that people minimize when they train a Bayesian neural network with variational Bayes. And there too, like people have observed that these things have problems. But if you throw back in a coefficient and you explore a trade-off between those two terms and you allow yourself sort of more freedom, you can often correct for those things. And really, I guess the story is if these are all sort of corners or edges of a single kind of space of solutions that explore trade-offs between these things, then really it seems like we should do a better job of exploring more of the space, because we could correct for kind of mistakes that we see these things make in certain limits. And I think I'm kind of basically out of time, but I could highlight maybe just sort of a couple of them, give you a little bit more intuition about what, I don't know if it's worth it. How about that? At this point, I will stop and ask if there are sort of natural questions, and then we'll see if any of that actually landed, and then if so, we can talk about stuff. If that was all very confusing.
So, can you hear me?
Yes, I can.
Yeah. So it's not actually a question, more like a classification. So, when you were talking about those like turtle pictures and that related function and output, like the output as turtle. So, if I consider a picture, so it has some arrangement of the pixels, right? So at some point, we are going to put some restrictions that, okay, these distributions are actually like represents turtle, and for that only the neural network will give the result at turtle, right? Outside of that, it just doesn't make sense. Is it that? Am I getting right thing?
I'm not sure. I'm not sure I'm following. In this kind of broader setup, the pieces that I'm allowed to control are just sort of on this half of the diagram. I can adjust my learning algorithm, and I can adjust sort of the architecture of my neural network. Oftentimes if I have a particular application, like, the difference between building a hot dog classifier and building a turtle classifier is, in the one case you've got images of turtles, in the other case you've got images of hot dogs. And I sort of don't get to control that part. But okay. I can still, even with that part fixed, so that part is, sort of.
Yeah. So my, I think my question will be in that case, so looking at the images, the neural network tries to find out the constraints, right? And then when it's trying to quantify it, it tries to identify on its own, outside the training set, then it applies the constraints to the pictures and tries to find out whether that matches with the pictures, those constraints matches with the pictures or not. Is it like that?
Yeah. The reason people train neural networks is that they hope that if they can find one that does a good job on 10,000 examples, that when they present it with the 10,001st example, it also does a good job. But actually, you have now just perfectly led me into why you might care about exploring these trade-offs at all. So, thermodynamics is a story about trade-offs. It's about exchanging, you get to increase the average in one quantity, you have to decrease the average in some other quantity, right? This is a surface, it's a convex surface. Moving up in one direction kind of moves down in the other. And why would you want to explore that sort of trade-off? Why, if what you care about is just the best possible predictions, why don't we just do what we said and kind of find the best possible predictions? And there, it's because there's, I think, like you point out, there's a subtle difference between achieving the best possible predictions on the first 10,000 examples and then achieving the best predictions on the sort of 10,001st example. And that's what we observe. So even in the context of something like classification in our sort of VIB, variational information bottleneck, if you kind of look at the corresponding one-dimensional surface, you end up, you see that there's this I'll remind you is classification performance. This is how well you can predict. This is error. Think of, better is smaller is better. And this was some measure of how complex the neural network was. More complex networks always do a better job on the training set, on the examples that you provided. That's just a given. Like that sort of has to be sort of convex in that way. But when you move to the test set, when you show it the next 10,000 examples, it so happens that more complex neural networks tend to perform worse. They overfit. And so part of why these trade-offs are so useful is that when we apply constraints, in particular, when we apply constraints on the complexity of, let's say, the output of the neural network or the complexity of the learning algorithm that sets the coefficients of the neural network, we oftentimes do a lot better on the sort of next 10,000 examples, because simpler representations and simpler learning algorithms generalize better to unseen examples or generalize better to slight shifts in the distribution. And we sort of see that not only in terms of test performance, but even in terms of modifications you can make to the images. So there are these this data set called common corruptions where people train on a large class of large-ish images for image classification. You're supposed to be able to say that this is some kind of finch. But then traditional neural networks, if all you do is minimize, in the one direction along C, they can learn very complex representations. And those very complex representations can be fragile in the sense that I can perform subtle variations of the input image. And as a human, you have sort of no trouble telling that each of these are images of finches. But for a sort of standard neural network, they can get very, very confused. And just adding a little bit of noise can make it decide that this is definitely a gorilla. What we observe is that if we kind of, again, we explore this surface of solutions and we kind of make trade-offs and we learn compressed representations, we actually become much more immune to these kinds of perturbations. And the networks that we train are much less likely to get confused if you kind of perturb the image a little bit. So that's in practice, most of the gains that we see on these problems, I think, are precisely because by exploring these trade-offs, and in particular by kind of exerting pressure on the complexity terms, we tend to learn simpler representations, simpler functions, and those actually do better in the future on the test set.
I had a small question about the thermodynamic nature of these cost functions. Could you comment on how do these quantities scale with the number of elements in the state space? So should I be thinking of them as extensive quantities? Do they scale linearly with the number of parameters, for example?
Right. So yes. So in normal thermodynamics, I think there was a very clear distinction between the sort of extensive and the intensive variables, where we talk about extensive and intensive variables as being the ones that scale linearly with the system size versus the ones that don't. I don't think that's the right distinction to draw, right? When we were talking about it earlier, I think the right distinction is there are state functions, things that are well defined for a single state, and then there are other things, and the other things are actually Lagrange multipliers. So it's clear to me, at least, that the derivatives on the surface aren't defined if you're not on the surface, whereas the state functions clearly are. Now, these functionals are state functions in the sense that I can measure them given any value of the distributions. I don't have to be on the surface in order to evaluate them. Meanwhile, the coefficients associated, all of the Greek letters in this objective are like sort of temperature and pressure and chemical potential. They're defined to be the derivatives on the surface, and they're not well defined for an individual state. Now, in detail, part of why I'm playing this game and not answering your question directly is because these things don't uniformly scale with n, or there's different n's involved. Like this functional, if I increase the number of parameters in my system, tends to increase linearly with the number of parameters, whereas these ones increase linearly with the amount of data I have, and this one increases linearly with the dimensionality of the output of my network. So they all scale and they get larger as the system grows bigger, but sort of because we have more moving parts, because there's sort of, more partitionings of the state in the machine learning picture, we have different notions of extensivity. And so I think the clearer thing is just there are state functions. There are things that if I give you if I give you a value of the state, you can sort of calculate exactly, versus things that you can't.
Thanks.
Yeah, I also have a question.
Yeah.
I just found that in fact in thermodynamics we have a concept which is called the fundamental thermodynamic relation. For example, we can express this relation in terms of the internal energy and the entropy and maybe the volume. I'm just interested in whether there is a similar concept in your new version of thermodynamics.
Yeah. So yes, thank you. Unfortunately, I deleted the slide, but just like in so just like in thermodynamics, right? In so much as we're describing things on the surface, the distributions over states that live on the surface have a sort of description. They are generalized Boltzmann distributions. Now, if you have a generalized Boltzmann distribution, you can kind of like stick this formula back in. You can calculate, oftentimes, you can calculate in closed form, like the entropy of the system in terms of the average energy and volume and pressure. And you can just kind of see that, like stick this into, I guess said another way, like this distribution, if you calculate the KL divergence between this distribution and Q, you can kind of evaluate that and you can maybe see it, right? If you remember, KL is P log P over Q. It's the expected value of log P over Q. If I take log of this over Q, the Q's cancel, and I'm left with the log of the exponential of the sum of the things, that the expectation eats them, and these are just the sum of the expected values of all the state functions, plus log Z. Log Z is the partition function. And I think you can already see that like the same sort of relation holds. Now, that's in the thermodynamics, but the story's the same. Like in the sort of machine learning paradigm, in so much as I am actually trying to describe a system that lives on the surface that I described, those distributions have simple forms. They're sort of Boltzmann-like. And for those distributions, I can write down relations between expected values of each of the state functions that hold. And I can do all the same geometry. I can write down Maxwell relations. I can write down, kind of first and second laws, these kind of total variations. I can write down I can describe things like the Legendre, not Legendre, the other one, free energies versus Helmholtz free energies, Gibbs free energies, things like that. That all still works.
I see. Thank you.
Yeah.
Yeah, I have a question about the four functionals. I'm just wondering kind of how you arrived at that set of four, and if you're claiming that that's like kind of an exhaustive set of things that you would care about in a situation or not.
Yes. So I'm not going to claim that they're exhaustive. I am only going to claim, I think that they're useful and they have sort of good coverage. At least they can cover a lot of papers. How did I find them? Really, I think the general story is sort of this one. Like in the context of sort of machine learning, right? There are like Bayes nets. There's these you can write down these. You can encode a set of relationships between random variables by just drawing these sort of diagrams with arrows. And ultimately, the whole apparatus sort of takes as its input just two diagrams. You draw one diagram, which is sort of honest in the sense that it describes what you actually do, right? And here I tried to describe what we actually do. The universe gives rise to images and labels, and then I have a learning algorithm that sets my parameters, and then I use an image and the parameters to produce an output. And then you choose another diagram, which is just your target. And this is sort of what you want. And this is often what Bayesians start with. It's the sort of modeling assumption. It's what you wish were to be true. You wish that your latent representation is actually the sort of generative factor for both the labels and the images. And just given two diagrams, you can ask the question, if I take a distribution that comes from this set of relationships and I minimize the KL divergence between it and a distribution that comes from this diagram, I can go even further and I can ask not just what's the KL divergence between this a distribution from this world and a distribution from this world, but what's the minimum possible KL divergence between a distribution from this world and any possible distribution from this world. And that has a well-defined answer, and the answer is just a sum of a bunch of mutual informations. This is the multivariate information bottleneck. And so yeah, so given any sort of set of two diagrams, you can kind of just turn a crank and you can end up with a set of, I think, more or less complete functionals describing the amount of disagreement between what you actually built and what you said you wanted. And this always takes the form of mutual informations, and then you can variationally bound these to make the whole thing tractable. And that was probably a lot of jargon, and I'm not sure it helped, but
yeah, that helped. Thanks.
Yeah.
Could I ask a question about related to the question from Didi Wong about the fundamental functions? I mean, if you're thinking in thermodynamics about, for example, the energy as a fundamental function, its variables would be in a simple system, the entropy, the volume, and the number of particles. Now maybe if somebody like Isaac Newton was thinking about the energy, he would certainly imagine that if you had a bunch of particles and they were in some volume, the energy, which he knew all about, would be a function of those two variables. The one that he might not know about was the entropy, and we now know that that's very important. So I guess my question is, some of these machine learning algorithms that you described, I got the impression that you were saying that they only take perhaps two dimensions in that space that really should be three, and there was an important one, the entropy, that maybe Newton didn't know about. And is that kind of the case? And you're saying that we really need to have at least 4 variables to define an interesting state that we then look for its absolute minimum. It has convex or concave properties. If you know those right number, and some of the other standard machine learning algorithms only do subsets of those and leave out some important direction. Is it a little bit like that?
Yeah. So I think yes. So I guess I want to make a distinction. So really, like, entropy or the KL divergence is sort of the unique new member to the party, right?
Yes.
So in thermodynamics, we had the state functions, and like whether you have energy and volume and number of particles, or energy and volume and number of particles and magnetization, like what you choose to be the extensive variables, I think of as, in this language, just a choice of which kind of constraints you're interested in measuring or applying. I could imagine some magnetic liquid where I just describe it as a USV system. I could imagine describing it as a USVM system. I could, et cetera. So those are the state functions, right? Because given the particular configuration, the entropy is the new thing. It's not I really don't think, it's not a state function, because it's not defined for a particular value of the configuration of the system. The entropy was a functional defined for a distribution over states. And that was the one that was unique, and that was the one that has interesting mathematical properties. It's guaranteed to be convex in its argument. And that's the one that guarantees that we have a surface. The surface is precisely those states that are, maximum entropy or minimum KL, given constrained values of anything you're interested in measuring. So yeah, I think, what did Newton miss, right? Newton missed that instead of trying to describe, what was the story? Instead of trying to describe the microscopic configuration of the system and running Hamiltonian dynamics, at some point, the whole thing gets too complicated. And the way that we go forward is, we give up on being able to describe a precise state of the system, and we instead try to describe the distribution over states that the system might be in. And the key insight is that, what Shannon and Boltzmann keyed us into is that you can then quantify what it means for that distribution to be sort of complex. And nature drives systems towards simple ones. And in the same way, I guess, this identification in the machine learning thing, we have KLs in there. It's for the same reason I'm trying to come up with algorithms or objectives that will drive systems towards simple solutions that still achieve, the constraints that I'm interested in. Now, it's not unique in the same way that, I could add additional things. I could imagine describing a magnetic liquid not just in terms of its volume and its energy, and its magnetization. I could also describe the tilt of the bed, and that would be a new sort of extensive variable I could add to the equation. You know, anything that I'm willing to measure, I can kind of throw into the mix. But there's kind of one special one, which is this sort of KL divergence, which is a measure of ultimately the complexity of the distribution over all possible states that I'm trying to find.
Right, but the viewpoint taken by, for example, Elliot Lieb and people like that was that while what you were saying is more general, and I think is probably the new thing that I really need to think about, but they were emphasizing that to some extent, thinking about entropy using only equilibrium states. It's complicated enough. This was kind of Lieb's general framework.
Mm-hmm.
It's complicated enough if we just talk about equilibrium states, and if you do that, you can still define what you mean by entropy, and so forth, and maybe we need axioms only for the equilibrium states, and we'll leave it to another generation to figure out what happens next. So from that point of view, the entropy, the energy is a fundamental function in this picture, is a function of thermodynamic variables, of which S is one for an equilibrium state, as we now know, although it takes into account all these things that you were saying.
Yeah. So I guess like, so, and I think this, you know, my opinion of this has changed a lot since going to sort of machine learning. But honestly, I think it's in some sense simpler rather than more complex. Not to, so first, yeah, I agree, right? And if we only consider the surface, yes, then, you know, there are ways to define like a thermodynamic entropy, which really would be like a state function. But yes, honestly, I feel like it is now, having kind of drank the Bayesian modeling, the probabilistic modeling, the sort of machine learning kind of way of thinking about things, I think it's actually easier to not do that and consider this whole space. Now, there's nothing mysterious about a non-equilibrium state. It's not a state. There are non-equilibrium distributions over states that live in the sort of bulk of these diagrams. And there are things that live on the surface. And sort of, I don't know, at least in my head, everything is making more sense now. Like now I can define, you know, state function values for these non-equilibrium distributions. I can't define, any of the Lagrange multipliers, temperature, pressure, chemical potential, because it's not on the surface. It doesn't have derivatives. And I think that's actually, like, I feel like a lot of the confusion, sort of both philosophically and like mathematically, that arrives in thermodynamics is precisely because, you know, we've for so many years been trying to limit the description to just describing things that are happening on the surface, and that it's real confusing real quick. I
have to say, I really like this other viewpoint, and this is what I teach, but I'm beginning to agree with you too, that it probably is not the easiest way to think about it. To me, one of your most provocative statements was that the extensive variables can be defined just in general, but the derivatives are defined only on, the intensive conjugate variables are defined only on the equilibrium states. But right, and I believe that's just what you said, if I understand.
Yeah. No, yeah, and I think that really is just. It's just
I hadn't thought about that before, in that way. Yeah, that's a pretty interesting point.
Yeah, and honestly, I think the time is actually honestly right for a confluence between the two fields. Right?
Yeah.
Like even, you know, Chris Jarzynski.
Yeah.
The Jarzynski equality is something that, you know, fantastic breakthrough, right? Like one of the sort of, you know, best ideas to happen in, you know, statistical mechanics for a long time. And I think, you know, I imagine, we could ask Chris, but I imagine it was very difficult to like come up with, right? Because it's really like a mind twist with regards to sort of the normal way that we think about thermodynamics and statistical mechanics. But in the sort of like probabilistic modeling world, around the same time, Radford Neal, you know, came up with a Neal's importance sampling, and sort of like the it's much easier to understand why it's true, because honestly, like annealed importance sampling, like it becomes just like a mathematical fact that's sort of unimpeachable, and it's almost like trivial to prove that you can form an unbiased estimator of the partition function given, you know, the ratio of the forward and backward probabilities. Like it just falls out. And so I really think that there are things that are easier to kind of prove and think about if you adopt this sort of probabilistic first perspective. And now what I'm kind of excited about is I think like both fields could really benefit from this. I think things that are hard to think about in physics are easier to think about if you sort of translate into the language of probabilistic modeling. And then similarly, right, like physics has made a tremendous amount of progress in,
Yes.
you know, actually like thermodynamics, system mechanics, and making like the world do our bidding. And if we could take some of those algorithms and results and ways of driving things and use them to make our neural networks better, that, you know, I think there's a lot of low-hanging fruit there too.
Okay, so I'm going to use my privilege as the organizer of the seminar and ask one question, and then we are going to call it a day, I think. So, Alex, really nice talk. Now, one of the things I wanted to ask you, so you say machine learning here, but the way you presented all of it was really in the context of static, non-temporal data, classification problems and things like that. It was not time series prediction, right?
Right.
But in thermodynamics, we have the same thing. For example, when we teach thermodynamics, we tell them, look, there is no dynamics here. It's all static. It's all like equilibrium. But thermodynamics has simple ways to go from thermodynamics to dynamics. There are theories that exist, for example, looking at a master equation or just looking at transition state theory, this or that. So the 4 state functions that you introduced, the distortion, this and that, or more generally, the information bottleneck principle, do you see simple ways of going from there and trying to discover machine learning algorithms, next generation algorithms, which can also deal with time series based on that principle?
Yes, as of September 3rd, yes, in the sense that your colleagues at Google actually kind of took the same story. They started with a different set of diagrams that, I agree with you, right? Like so far, the story that I kind of worked out and tried to describe was in the sort of static case. They just extended the diagrams to sort of include actions, right? Like in a reinforcement learning kind of context. Now, not only is the data not potentially static, but I can take actions that actually influence the data, right? That's what happens in reinforcement learning. Now, actions that the agent takes can actually influence the future. But they similarly just kind of like wrote down kind of 2 diagrams. They minimized AKL. They looked at the kind of terms that describe the amount of disagreement. And this paper, Action and Perception as Divergence Minimization, is kind of that same story, but for the context of reinforcement learning. And yeah, like can describe kind of all of, a wide range of the existing reinforcement learning algorithms that people have already invented, as well as like for free, all of the kind of algorithms that live in between. And also sort of naturally in a limit reduces to the static case. So this is sort of like a strict, expansion of the ideas that I have here. And I think it precisely starts to address the, what you said, like the non-static case.
Okay, Chris, did you have a question?
No, I just
okay.
on my mic. I mean, I would agree about the big overlap between some of these kind of statistical methods and the physical methods. And it's true that the 2 fields do have a lot to learn from one another. So.
All right. So on that note, once again, let's thank Alex very much for a really unique and interesting seminar. And I hope we can have more of this in our statistical physics seminar series, which has been running for more, I don't know, maybe 3 decades. And I think in this year, we have really started to think more and more about machine learning, because we cannot avoid, as seen from today's talk, that there is a lot to be gained from statistical physics. So Alex might have 1 or more 2 slots left to meet people. You can email me, ptiwari@umd.edu, if you're interested in meeting. I cannot promise that the slots are empty, but if they are, I will put you in touch with Alex. So please join me in once again thanking Alex, and hope to see you soon again, Alex.
Very nice talk.
For my part, thank you guys so much for inviting me. And I would love to chat with people more. Feel free to reach out to me, take one of the slots, or otherwise, try to write an email. And I don't know, I really would, I came from physics, but I feel like, my physics muscles have started to atrophy, and I really do think that there's potential for, the 2 fields learning from each other and stuff. And
we can send you our thermodynamics homework problems if you have that problem. All right. Thanks everyone.